In this video, we're going to derive the relationship between pressure and depth, which is the foundation of everything in hydrostatics. The problems of static fluids are much simpler than those associated with the motion of fluids. Exact analytical solutions are possible. Hydrostatics considers a fluid at rest, so there's no shear stress, which means that all the forces on a body in a fluid are normal to its surfaces. Forces due to standing water are important in structures such as reservoirs, dams, locks and sluices. Even in moving water with a free surface, such as rivers, canals and floodplains, the pressure distribution can be assumed to be hydrostatic. Before we derive the fundamental equation of hydrostatics, we need a couple of definitions. First, we have the notion of pressure, which is defined as force per unit area. The SI unit for pressure is the Pascal, where 1 Pascal equals 1 Newton per metre squared. Two other units are routinely used for pressure, the bar and the atmosphere. 1 bar is 10 to the 5 pascals, and 1 atmosphere is 1.013 bar. The atmospheric pressure at sea level is equal to 1 atmosphere. It's worth noting that we often measure pressure relative to atmospheric pressure. What we call the gauge pressure is excess over atmospheric pressure. Okay, so let's take a closer look at pressure. The pressure at a point on a plane surface is defined as the limit of the ratio of normal forces on the area as the area approaches zero at that point. From this definition, we can deduce Pascal's law, which states that the pressure at a point in a fluid at rest is the same in all directions. Let's have a look at where that comes from. Consider a small triangular prism of unit length within a fluid at rest. Since the fluid is at rest, the sum of the forces acting on that prism must be zero. If there's any unequilibrated force, the fluid will flow. Thus, if we consider the forces in the horizontal and vertical directions, we have sigma Fx equals 0 and sigma Fy equals 0. Let's consider first the horizontal forces. Well, we have P1 times AB times 1, which is the force on the left-hand face, and minus P3 times BC times 1, which is the force on the diagonal face, times cos theta, which resolves that force in the horizontal direction. Turning to the vertical forces, we have P2 times AC times 1, which is the force on the bottom face of the prism, minus P3 times BC times 1, which again is the force on the diagonal face, but this time times sine theta to resolve in the vertical direction, and minus W, which is the weight of the fluid in the prism of water. If we look at the geometry of our prism, we can see that cos theta equals length AB divided by BC, and sine theta equals AC divided by BC. Thus, we can deduce from the horizontal forces equation that P1 equals P3, and from the vertical forces equation that P3 equals P2 minus W divided by AC. Now, the purpose of this analysis was to look at the pressures at a point, so we take the limit as the dimensions of our prism shrink to 0. In the limit, the weight will tend to 0 and thus P3 will equal P2. We have thus shown that P1 equals P2 equals P3. Remember that we made no assumption about the size of the angle theta, so we can be satisfied that the pressure is the same in all directions. So, hydrostatic pressure at a point is equal in all directions. But what about hydrostatic pressure at different points? Well, the hydrostatic pressure at different points within a body of fluid is not equal. We'll see that pressure increases linearly with the depth of the point. Before we prove that result, we need another definition. Density is defined as mass per unit volume. We usually use the Greek letter ρ to denote density. Water has a density of approximately 1,000 kilograms per metre cubed, and we often state the density of other fluids as a relative density. In reality, the density of water changes with temperature, as we can see on this graph, which plots temperature against the density of pure water. Okay, so now we have all we need for our next proof. Consider an elementary volume of fluid, in this case a cylinder with length delta L, cross-sectional area delta A and weight W. Since we are interested in how pressure varies with depth, we take this elementary volume to be inclined at an angle theta to the horizontal. As before, the fluid is static, so the sum of the forces on the elementary volume must be zero. For simplicity, I'm going to look at an axis running through the centre of the cylinder, which I'll label as the x-axis in this case. We know that the sum of the forces along this axis must be zero, i.e. sigma f of x equals 0. So, what are the forces? Well, there's the weight of the fluid, which is denoted W here, and there are the pressure forces at the ends of the cylinder. Remember, we know that the forces are perpendicular to the surface of the cylinder, so the pressure forces along the length won't contribute to the forces in the x direction. I'll label the pressures at either end as P and P plus delta P. Now we can resolve the forces in the x direction. You might want to pause the video for a moment here to jot down what you think the forces are in the x direction. What did you get? Well, the only thing missing from our diagram is the x component of the force due to the weight of the fluid in the cylinder, which will have magnitude W sine theta. Thus, we have P delta A minus W sine theta minus P plus delta P times delta A equals 0. The two P delta A terms cancel each other out, and we are left with delta P times delta A equals minus W sine theta. Now, the weight W is going to be the fluid density times acceleration due to gravity times the volume of the cylinder, and the volume of the cylinder is simply delta L times delta A. Thus W equals rho g delta L times delta A. Substituting W into equation 1 and dividing both sides by delta A, we get delta P equals minus rho g times delta L times sine theta. If we look at the diagram, we can see that sine theta is delta y over delta L, so delta P can be written simply as minus rho g times delta y. If we now let delta y tend to 0, making our elementary volume shrink to a point, we can see that the gradient dp by dy equals minus rho g, which is constant provided our fluid has a constant density. Integration yields the equation P equals minus rho gy plus a constant. Now, if we want to have an equation that's usable, we need a value for the constant of integration C. So let's think about what the distribution of pressure looks like in a fluid with a known base and free surface. We can formulate a boundary condition for this case. If we let the bottom of our domain be the datum for y, and let y0 be the depth of the water and p0 the atmospheric pressure, then our boundary condition is P equals P0 when Y equals Y0. What does that make C? Substituting these values into our equation for P gives P0 equals minus rho g Y0 plus C, i.e. C equals P0 plus rho g Y0. Putting C back into the equation for P, we get P equals P0 plus rho g Y0 minus Y. If we consider an arbitrary point a distance y above the datum, then y0 minus y is the distance of that point from the fluid surface. If we denote that distance h, then our equation can be written P equals P0 plus rho gh, or simply P equals rho gh above atmospheric pressure. Most of the time we take it as read that we are measuring pressure relative to atmospheric pressure, and we simply write P equals rho gh. This is an important result because it means that the hydrostatic pressure depends only on the vertical distance of a point from the free surface of the liquid. This in turn means that if we have liquid in a container, the hydrostatic pressure doesn't depend on the shape of the container or the volume of fluid in it. It depends only on the density of the liquid, the water depth, and of course the acceleration due to gravity. Thus, the pressure at the bottom of each of these containers will be equal, because the fluid depth is equal in all 5 containers. Let's check the units of our equation. ρgh has units of density, kilograms per metre cubed, times acceleration, meters per second squared, times depth, meters. This simplifies to kilograms per metre second squared. This can also be rearranged in the form kilogram meters per second squared times 1 over metre squared, which yields newtons per metre squared, which is pascals as required. Let's have a look at what the pressure distribution looks like. Since h is the vertical distance below the fluid surface, we plot the h-axis downward and the line h equals 0 corresponds to the free surface of the fluid. Plotting p horizontally, we thus have the straight line shown here, which has gradient ρg. This is often represented as a pressure diagram as shown here, where the red arrows indicate the magnitude of the pressure at a particular depth. Pressure diagrams are also often shown like this, without the axes. Or like this, with horizontal lines representing the pressures. We can rearrange our equation to give h in terms of p, ρ and g. H is known as the pressure head, and it is expressed in meters of fluid of a given density. The expression for hydrostatic pressure can be rewritten as p over ρg plus y equals y0, which is constant for a fluid at rest. This shows that any increase in elevation is compensated by a corresponding decrease in pressure head. Such a distribution of pressure is known as a hydrostatic pressure distribution. The constant depth y0 is called the piezometric head, a term we use both with a standing fluid and a fluid flowing with a free surface. It's worth noting that when we have fluid confined in a pipe, we still have a hydrostatic pressure distribution, and this provides the basis for one method of measuring pressure, the piezometer.